Hello, I am Anthony Kim, and I am from Massachusetts, United States. And I would like to start my presentation on the development of eco-friendly deicer using the Macropore scaffold structure of oyster shell waste. Climate change is a serious global problem in our modern world driven by technological advancement. The yearly global temperature has continued to rise since 1880, the year when reliable temperature record keeping began, at an average rate of 0.08 degrees Celsius per decade. The earliest recorded the hottest year is 2005, and the past decade has witnessed extreme patterns of rising temperature, causing numerous devastating consequences related to climate change such as droughts, heat waves, floods, and storms. Heavy snowfall is one of the major problems related to climate change. With the rising temperature, more water evaporates into the atmosphere, and considering that for every 1 Fahrenheit increase in temperature during the winter season, the atmosphere can hold 4% more moisture, heavy snowfall increases unless the temperature rises above the freezing point. In 2022, around 3.7 billion kilograms of oyster shells litter as waste daily worldwide, leading to the pollution of soil and water. Oyster shells pose a huge problem for the environment because they do not decompose and remain as waste. The commonly used de-icing agents are made from rock salt, and calcium chloride and sodium chloride serve as effective de-icers. However, these chemicals damage cars and roads as well as plants and animals. They have corrosive properties and penetrate the ground to increase the salinity of water and soil, and impurities in these de-icers can also become the source of pollutants. The experimental design involves the following process. First, the structure of the oyster shells is observed. The oyster shells are prepared as de-icers. The biosafety of the prepared de-icer is tested, and the effectiveness as de-icer was evaluated. First, the oyster shell powder was purchased from SSD Food, and the structure of oyster shells was observed at various magnifications, from 7 times to 400 times, using a stereo microscope and an inverted microscope. There are 2 types for preparation of oyster shells as a de-icer. One method is based on heat treatment, in which the oyster shells were heated at 1,200 degrees Celsius for 10 minutes and grounded. The other method is the salt coating method, in which the sea salt and oyster shells are mixed at various ratios. With this method, different names are given depending on the proportion of sea salt and oyster shells for coating. OS stands for oyster shells, SS stands for sea salt, and the number in the middle indicates proportion. For example, OS1 SS1 refers to a mixture of oyster shells and salt in a 1:1 ratio, and OS2 SS1 is a mixture of oyster shells and salt in a ratio of 2:1. To examine the applicability of oyster shells as a de-icer, the ice melting rate and metal corrosion characteristics were analyzed and the biosafety of oyster shells were tested. First, the metal corrosion characteristics were tested by exposing a metal rod to an environment close to the real-life setting. The metal rod was inserted into soil, snow was sprayed and left to be melted using different de-icers, and then the metal corrosion characteristics of the de-icers were analyzed. Biosafety tests was performed in 3 parts. Tests were performed on earthworms, cells, and plants. In tests with earthworms, 10 earthworms were used for each test condition, and the overall health state of the earthworms was tested after exposure to the different de-icers. Cell safety was tested using immune cell DALI, and the cell viability was measured after exposure of the cells to various de-icers. RPMA 1640 was used as a medium for cell culture. For testing plant safety, de-icers was mixed in the soil with the plant growing, and the plant was cultivated in soil under the same conditions, apart from using different de-icers. Over time, the occurrence of problems in plant growth was observed. As for the analysis of ice melting rate, ice cubes were used at room temperature, and the weight of each ice cube was measured before and after exposure to different de-icers. In the case of 4 degrees Celsius and negative 20 degrees Celsius, the weight of melted ice was measured using ice powder. Now, let me present the overview of the results of the above analyses. The results will be discussed in 3 main steps. First, the ice melting performance, biosafety, and the metal corrosion characteristics of oyster shells will be analyzed. Second, the result of the feasibility for the development of oyster shells as de-icer. And third, the importance of the detailed information on the structure of oyster shells. First, I examined the applicability of oyster shell powder as a de-icer. Table 1 shows a comparison of ice melting performance between oyster shells and sodium chloride. At 4 degrees Celsius, the ice melting performance of sodium chloride was excellent, but at negative 21 degrees Celsius, the ice melting capacity of oyster shells was nearly twice superior to that of sodium chloride. At room temperature and 4 degrees Celsius, the ice melting rate of oyster shell de-icer was similar to the control, but at negative 21 degrees Celsius, it was more effective than salt, a commonly used de-icer. Then, I compared the biosafety of oyster shells with other de-icers. First, as for safety testing for earthworms, from Table 2, it can be seen that when the earthworms were exposed to de-icers, All 10 of them survived with exposure to the control and oyster shells. For the other deicers such as abalone shell, sodium chloride, and calcium chloride, all or some of the earthworms died, indicating toxicity for earthworms. The oyster shell showed almost no effect on plant growth. As for cells, as seen in Figure 6, oyster shells showed slightly higher toxicity compared to the control, but when compared to salt, oyster shells showed a significantly lower level of toxicity. In addition, in terms of metal corrosion characteristics, oyster shells showed a surprising result of reduced metal corrosion. As you can see from Figure 7, with the level of metal corrosion of the control as a reference value at 100%, the level of area for no metal corrosion for oyster shells was 110.9%, confirming a decrease in metal corrosion. As for the observation of structure of oyster shells, as shown in the photo in Figure 8 and 9, small holes can be seen and porous structures are visible. In comprehensive consideration of all of the factors discussed so far, I decided that the oyster shells have the potential for development as a deicer and continue further research. For the development of oyster shells as a deicer, OSR-SS1, which is a mixture of oyster shells and sea salt in a 5:1 ratio, showed the best performance. From Table 3, it can be seen that the salt-coated oyster shells show superior performance to salt in terms of the ice melting rate, regardless of the ratio between oyster shells and sea salt. However, in the biosafety test, Table 4 shows the survival rate of earthworms. When the test was performed with OS5-SS1 and OS2-SS2, which is the ratios that showed the best ice melting performances. In the case of OS5-SS1, all earthworms survived, and with OS2-SS1, all earthworms died. The oyster shell deicer showed no specific effect on plant growth. From Figure 10, in the case of cell testing, less toxicity was confirmed with all ratios compared to salt, but there was no significant difference in terms of toxicity between different ratios. For other ratios, all aspects other than the safety of earthworms showed equivalent results, but in the biosafety test with earthworms, safety was confirmed only with OS5-SS1. Therefore, it was determined that OS5-SS1 was the best deicer. In terms of the metal corrosion characteristics, it was first expected that the corrosion will increase since the oyster shells are mixed with salt. However, as can be seen from Figure 11, which shows a comparison of metal corrosion characteristics, it is inferred that the porous structure of oyster shells inhibited corrosion, and oyster shells show similar corrosion characteristics to those of the control sample. As a result, I concluded that the porous structure and sea salt match well, complementing each other. The importance of structure was confirmed in the experiment with heat-treated oyster shells. Heat treatment was performed to remove calcium carbonate contained in the oyster shells. I performed experiments to examine if the ice melting performance improves when oyster shells were heated at 1000 degrees Celsius to remove more calcium carbonate. When the heat-treated oyster shells were ground, it could be seen that the heat-treated oyster shells exhibited a higher ice melting rate compared to those without heat treatment. When the heat-treated oyster shells were coated, as can be seen from Table 6, the ice melting rate of non-treated oyster shell powder with coating was faster than those without heat treatment. Since the ice melting performance showed a considerable degradation when both the heat treatment and coating were performed on the oyster shells, the performance was lower than that of oyster shells with coating only, and also inferior to that of salt. When comparing the oyster shells with and without heat treatment in microscopic observation, for those without heat treatment, rough surfaces and small holes were observed. This is the porous structure of the oyster shells. When I observed the heat-treated oyster shells, smooth surfaces and no holes were observed. It is inferred that the porous structure has disappeared or been damaged. From the result that the ice melting rate decreased when no porous structure was observed, it can be confirmed that porous structure plays an important role in ice melting. A porous structure can be observed in the oyster shells, and experiments have shown that the structure lowers the salinity and enhances the ice melting performance at lower temperatures. Using this knowledge, oyster shells were coated with sodium chloride so that with the porous structure of oyster shells, both a decrease in toxicity and an improvement in ice melting performance can be achieved. OS5-SS1 showed longer-lasting de-icing performance and more efficient de-icing at lower temperatures. Metal corrosion was reduced to a level similar to that of control, and biosafety testing was conducted to conclude that the oyster shell de-icer was safe. Oyster shell de-icers can be easily applied for real-world de-icing and is highly useful. The development of waste oyster shells into de-icers can reduce the waste oyster shells, and the de-icer can contribute to public safety in the event of heavy snowfall. Furthermore, OS5-SS1, an oyster shell de-icer, is very simple to prepare, so when it snows, I plan to get some oyster shells and seawater around the campus to coat the oyster shells and carry out testing with the oyster shell de-icer sample around the university site. Thank you.